Alright, so today we're going to be looking at a problem involving a channel of water. So our channel is going to be rectangular, and it's going to be at sort of an incline. So we'll have this channel, and it's going to have water flowing downwards. And then we can also show this from a couple of different angles. So from front on, we have, it looks like this. We just have a rectangle of fluid that does not go all the way up, and it is open to the atmosphere at top. And the width of this channel is W, and the height of the liquid within it is H. So then we can also have a side view of the problem, at which we can see the angle that our channel is at. And again, there's water flowing throughout, and this length is going to be delta x. But we also need to know the angle at which this channel is at. So we have the horizontal line here, the angle between this and the bottom of this channel is going to be theta. That's theta. And so we can also get at this length here, because we've got a right triangle. So that length here was going to be delta x times sine of theta. Alright, so next we can start to plug this into Bernoulli's equation. So this is a gravity-driven flow because both the pressure at point 1 here and point 2 here it's open to the atmosphere, so those pressures are equivalent, so there's not going to be a pressure difference. So when we have Bernoulli's equation, we have that the pressure at 2 minus the pressure at 1 over the density plus acceleration due to gravity times the change in z, which is height, and that's this distance right here. And that's equal to the frictional heating, which is also 4 times the fanning friction factor times delta x times v squared over 2d. Alright, so we know that this term is going to go to 0 because these two pressures are equal as it's open to the atmosphere. And then we are going to plug this value into here. And then we can divide everything by delta x. So we're going to have that g times delta x sine theta over delta x is equal to 4, or we can cancel this and just have 2 there. So 2 times the fanning friction factor times delta x v squared over d delta x. So these delta x's cancel, those cancel, and we've got that acceleration due to gravity times sine of theta is equal to 2 times the fanning friction factor times velocity squared over d. Okay, so next thing we want to consider is the shear stress that these walls exert on the liquid. And to do that, we are going to consider the same situation but for a cylindrical tube. And we're kind of going to make an assumption that this situation is going to be comparable when determining the shear stress. So in this case, we have a vertical tube filled with liquid, and the liquid is gravity-driven flow going down, in which the acceleration of this liquid is equal to 0, which means that there's a force balance, that the weight of the fluid is exactly balanced by the shear stress of the walls. So we can get at that by an equation. So we have, so first we need to get at the weight of the fluid, so we can find the volume. We're going to call this length here delta x. So volume here is area times delta x. And then, so that's our volume, so we're going to times the density, gives us the mass, times acceleration due to gravity gives us the weight of the fluid. And then that is going to be equivalent to the force. So this is the force going in the downwards direction, and this side is going to be the force going upwards direction, which is the shear stress times the area of which it acts over. So the area which it acts over is the perimeter, so the perimeter of this circle times the height, but this perimeter we're going to refer to it as the wetted perimeter, because we'll see here later this entire channel is not full of water, but here it is. So it will be the entire perimeter, but we're going to still refer to it as the wetted perimeter times delta x. Alright, so here you can see that delta x is cancel, and we're also going to divide area across. So we're going to have that rho times g is equal to shear stress times the wetted perimeter over the area. Alright, so now this wetted perimeter over area is a pretty important ratio that we can determine. So for this circular geometry, we have that the wetted perimeter over the area, so that's just the perimeter of a circle, which is pi d over the area, which is 2 pi r squared, or pi d squared over 4. So then this pi cancels that pi, and then one of these d's cancels, so then we have that this ratio is 4 over d. So then we can use this ratio here, this is where our assumption is being made that we can use this ratio here in relation to our cylindrical geometry to plug in here and get at the shear stress for our more complicated geometry. So doing that, we have, we're also going to solve for gravity here so that we can plug it in over here. So we have that our acceleration due to gravity is going to be equal to the shear stress over the density times this wetted perimeter over area ratio, which is 4 over d, which we found here. So from here, we're going to take this and plug it in down here. So here we've got that 4 times the shear stress over density times diameter times sine of theta is equal to 2 times the fanning friction factor times velocity squared over d. So you can see a couple things cancel out, so, or it's just the diameter cancels, and we can solve for, oh yeah, and then this coefficient also cancels. So we can solve for this tau by multiplying this rho over and dividing the sine theta. So we can have that the shear stress is equal to the density times the fanning friction factor times velocity squared over sine of theta. Or, oh, sorry. So over 2 sine of theta. There's that 2 up there. Okay, so from this part, we found our shear stress, and now we want to go back to this equation and solve it for this geometry. So I'm going to switch colors for us to try and make it a little bit more clear. So we need to find the wetted perimeter to area ratio for this geometry. So we can do that down here, where we have the wetted perimeter over the area. And so from that, we're going to look at this side most closely. So our perimeter is side length h plus w plus h, so that's 2h plus w, and the area is just h times w. Alright, so we can plug this and this into this equation. So we have that our density times our acceleration due to gravity is equal to shear stress, which is density times fanning friction factor times velocity squared over 2 sine theta, and then times 2 times the height plus the width over the height times the width. Alright, so then from this part, in our problem, we're not going to know what our velocity is, but we are going to know what our flow rate is. So we can get at this velocity here with the flow rate, and also these rows cancel. So we know that flow rate is equal to velocity times area, which means that our velocity is equal to flow rate divided by area, and as we just discussed, area is HW, so we can put HW there. And then we're going to plug this into here. So we have that the acceleration due to gravity is equal to fanning friction factor times velocity squared, so we're going to square this, and we got q squared over 2, it's kind of messy, so we've got fanning friction factor times q squared over 2 sine theta times 2h plus w over hw cubed. So this q squared over 2 of each hw's, that's this value right here squared because of the velocity squared, and then the other hw comes from right there. Alright, so this is the main equation that we're going to use to get at the height of the fluid in here. Because we know acceleration due to gravity, we know the flow rate, we know theta, we're going to know we're going to find h, and we know w. The only other thing we need to worry about is our fanning friction factor. So fanning friction factor is a function of the Reynolds number and the roughness of the surface, and Reynolds number is rho VD over mu. So we're going to know what fluid is going through there, so we know our density and our viscosity. Velocity we can find from this q. Diameter is the only thing that's not clear, because what exactly is the diameter of a rectangle? And we can get at that, again, using this wetted perimeter to area ratios. So we have this one and this one. So you'll notice for the circular geometry, this is dependent on diameter. So this ratio is just 4 over the diameter. So we can use this and this. We can set this, the wetted perimeter and area ratio for the circular geometry equal to the one for this rectangular geometry, and solve for diameter to get the approximate diameter of this rectangular geometry. So that's going to look like this. We'll have that 2h plus w over hw is equal to 4 over d. And we're going to solve and get that d is equal to 4hw over 2h plus w. And so that's the d that we can use right here. So yeah, these are the important equations we have here. And we will show how to solve these equations using Python momentarily. Alright, so next we're going to do the Python portion of our problem. And so we're going to be using the root function in Python to solve our nonlinear equation. So we've been given these specifics for our problem, where we have a width. So the width of our channel is going to be 0.5 meters. We're going to have a flow rate of 1 meter cubed per second. Our channel is going to be on an incline of 15 degrees. And then we're going to be using water. So our mu is 1 e to the negative 3 pascals per second. Rho is 1 e to the third kilograms per meter cubed. And of course, our acceleration due to gravity is 9.1. So first thing we do in Python, we're going to import our library. So we're going to import numpy as np, and we're going to from scipy.optimize and then import root. Alright, so next we want to input all of these constants we have. So we have W is equal to 0.5. We have that Q is equal to 1. Theta is equal to 15. Mu is equal to 1e to the negative third. And rho is equal to 1e to the third. And G is equal to 9.81. Alright, so there are our constants, and then we need to define our equations. So for root's going to take in a function, so we have to put all of our equations in a function. So we'll define a function, we'll just do EQ for equations, and it's going to take in a vector. And this is going to be a vector of our unknown. So root can solve more than one unknown at a time, but we only have one unknown in this problem, which is our height, so we just need to unpack that vector and have that our height is equal to the first value in the vector. Alright, so then from there we can start typing in some of these equations. So for example, our Reynolds number is going to equal rho times velocity times diameter divided by mu. Alright, and you can see we don't have velocity or diameter defined, so we can do that. So we have, from right here, we have that our velocity, we're going to have to do this above the row. We have that our velocity is equal to our flow rate divided by our h times, divided by h times w. Right, and then we need our diameter. So we'll have our diameter, that's from down here, is going to be equal to 4 times h times w, divided by 2 times h plus w. Alright, so then that should be all for now. So we're also going to need our friction factor. So for that we're going to define that outside, and we're going to take our function that we created for the friction factor back in homework 3, where I went through exactly how we came up with this function. We're just going to copy and paste it. Over here we use the Churchill equation to calculate this fanning friction factor. So yeah. Alright, so then once we have that in there, we can then say that our F is going to be equal to Churchill of our Reynolds number here that we defined as R, and then we need a reference value, so we can put that up here, and let's just say that it's 1e to the negative 6. So then we'll put that down here. Alright, so then now we should have everything defined, and we can return. That's the word I'm looking for. So we're going to return, it's going to need to be a vector. We're going to return our answer basically. So what root does is it sets everything equal to 0. So we need to basically set this equation equal to 0 by subtracting this side over to g. So it's going to be g minus this side is equal to 0. So we have g minus, alright, so then we have numerator, we've got f times q squared W. This numerator divided by denominator, which is 2 times sine NP sine of theta times H times W to the third. Alright, so then should have everything entered in, so now we can just use the root function. First thing we need to list in the root function is the function that we're going to be finding the root of, so that's our equation. And then we have to list an initial guess, so we can just guess 0.1 maybe, and we'll see what we get. Alright, so this is our solution converged. Alright, so this is our solution that converged, but it doesn't quite look right. Oh, it's because we put in, so theta is 15 degrees, and Python needs this to be in radians, or assumes that it is in radians, so we need to convert that to radians, where we have NP pi divided by 180. That should do it. Alright, so now we're getting a value that is about 1.4, or 0.14, which is about what I was expecting it to be, so yeah, so this is how we would solve for the height. So this value right here, this is our the height of the liquid within our channel.